Well, good morning, everybody. Welcome to Ellensburg, Washington. In the backyard. Represent. Hope you're all doing well this morning. The local time is 8:51 a.m. and we'll begin our program on hotspot volcanism at 9 o'clock. A short 9 minutes from now. Good morning, Belgium. Ooh, burned my tongue. Germany, watching live. Terrific to have you with us. Another Belgium. The Permian Basin. Olympia. Linwood, Puyallup. Mardine from Lake Lewis. The Netherlands. Hello, Noralie. Just kidding. I wish. New York City, Corvallis, Oregon, London, Canada. It's a pleasure to have you all with us. It is a beautiful sunny morning here. Rotterdam, good morning. Germany. We've been in the front porch the last few times, so it feels great to be back out. We still have a bit of a breeze, so I've got the house set up for the camera. And hopefully you don't hear a lot of wind whipping. I've kind of been pleased with this little shelter for the phone, so that's the goal. Croatia, good morning. That's the goal, to have Hungary. Wow, I love this. I just love this. I gotta love it, and I do. Montreal, Quebec. So it looks like we're functional. I guess I'll ask you directly just one time here. You're doing okay with audio, visual, buffering, stream quality, blah, bitty, blah, bitty, blah. 5x5, says the Collins Jackson family. Good. Okay, I got a couple thank yous for you, and we're also going to look at the schedule. Oh, and I got to check my laptop quick. Hang on. I don't know if we need... Yeah, that works. So this is the week that was. Slow earthquakes with Walter Zaliga. Still don't have the live comments. I think it was Jack sent me an email and giving me some tips on how to find that live chat and restore it, basically. So thanks, Jack. I kind of looked into it, and then I got chicken. I didn't want to screw the whole thing up, because the show is there. You just can't see the live comments, and Walter did such a nice job on Tuesday. So I'm still hoping to solve that. I might ask for a little bit more help if you are gifted that way. How can I find those live comments and get them to show up on that whatever live stream that was? We talked about Lahars in Washington and Rocky Crandall one more time. We talked about the Titan Andesite last time, even though we had a complete shutdown of the live stream, which I could not resuscitate. So we had a thing where we all jumped ship to a second live stream, and I kind of started over. And that's the one that remains in replay form. So hope you were able to jump with us. And if not, you'll be able to watch it live stream. So this morning, hotspot volcanoes, and tomorrow morning, Bing Crosby geology. Huh? Susan from Renton showed up yesterday and dropped off a wonderful gift. Perfect for today's discussion about Hawaii and other places that are exotic. So thank you, Susan. And one big box arrived in the mail. Very heavy box. $21 postage to ship from the Okanagan in Washington. So basically from Tonasket to Ellensburg. So that's an investment right there. So what's in the box? Rocks. Here's a wonderful serpentinite. It's been cut. The phone's in the house, so I can't use the zoom-in camera on the back this morning, easily at least. And all sorts of other rocks from northern Washington. And there's a card. Dear Professor Zentner, from the convergence of North Cascades and the Rocky Mountains, that's what I like to say, that's what John and Chris like to say, here are some rocks from our fields. They were just rocks, and now they're spectacular specimens. The small ones are for Muffler Boy. The larger green rock can be used as a paperweight. The beer can be used at your discretion. We enjoy your class immensely. Thank you, John and Chris from Tonasket. Would you read the dark bottle on the air? So there were 2 bottles of beer in with the rocks. Nice touch. Corona. Nice. And here's the dark bottle. This episode of Nick from Home brought to you by Polygamy Porter. You gotta love it. Why just have one? Polygamy Porter is a smooth, chocolatey, easy-drinking brown porter that's more than a little naughty. Take some home to the wives. Food pairings, anything goes. From Utah Brewers Cooperative in Salt Lake City, Utah. Thank you, John and Chris. We'll put the paperweight up here with the globe. All right, I got 1 minute to concentrate, and then we shall begin. Thank you for joining us. I'll be back in a minute. Well, a pleasant good morning to you all. Thank you for joining us this morning. This is a backyard in Ellensburg, Washington, USA, and I'm so glad that you could join us live, or if you're watching this in replay, hello from May of 2020. We continue with our live streams this morning, and the topic is hotspot volcanism. And we got two kids home for the weekend-ish in their 20s, and so it's been really wonderful to spend time with them, of course. Haven't seen them in a few months. So last night after the big dinner we had and doing the dishes, and I'm starting to think, okay, what am I going to do tomorrow morning with you guys? And I started sketching out a few things on a scrap piece of paper, and yeah, okay, I can do that, and I can do that. And, well, maybe I should try that, and they're probably going to ask about that, so maybe I'll look up a few things. And I found a video on YouTube, and I don't know if you know about this guy, Roman in Germany. I don't know anything about this guy, but he put together a program, a video, and I'll share portions of it with you this morning, that is everything I was going to do on that scrap piece of paper. So it's almost like I want to go, hey, let's just watch Roman's video for 17 minutes or whatever the heck it is. I won't do that. I mean, you're here to kind of have a little bit of this, and we'll do some live Q&A in a bit. But I'm so impressed with this guy, and I had seen some of his videos before, and I think I even emailed him once just to say great job. But what he has done will do a lot for us, but I think my job this morning will be to lay out some basics, lay out some things that we feel comfortable with, lay out some things that are still quite mysterious about these things called hotspots or mantle plumes. And then I think what I'm saying is I've got plenty in the Cozy Fort, not only Roman's video, but a few other little segments as well. Okay? So let's just do it. So we have volcanoes. Great, aren't you glad you tuned in? We have volcanoes. Case closed. Thanks for joining us, everybody. And here's some places that have volcanoes. You can vacation at every one of these places, except this one. You're like, I don't think I know what that is. But the others, have you been? I have yet to go to Iceland. That's on our list, of course. But I've been to Hawaii and Yellowstone and Galapagos. No big deal. That was a long time ago. And in many cases, and this has been observed for centuries, you know, you're an explorer out in the ocean, and you notice that if you look on a map, if you kind of sketch a little map, or as maps started to get more and more accurate worldwide, you have these out in the water, you're looking down on the ocean now, you've got these islands that are all lined up. And you know, let's say more than 1,000 years of people just kind of going, I wonder why those islands are all lined up like that. And a few of them are active. Like I put little red in here to indicate that there's lava coming out of some of these oceanic islands. And you're like, what is going on? Why are they lined up like that? Well, part of the answer is a mantle plume or a hotspot. But there are other places where we have this kind of string of pearls out in the ocean, and it's not a hot spot. So I think that's how I'd like to start. And of course, Roman did that. It's like, this guy's reading my mind, or vice versa, or something, I don't know. So what I've chosen to do here, I sketched it out, and then I saw Roman did it as well. Now I'm overboard on Roman. I hope that's his name. I just literally clicked on About on his YouTube channel. The YouTube channel is called Facts in Motion, pretty sure. And I just clicked on it About. He's got one little paragraph about himself. I know nothing about the guy. But he laid this out this way, and I loved it. And so I want to kind of do it the same way. So this is our topic, but we can also get these lines of volcanoes when we have subduction. We also have lines of volcanoes when we have a seafloor spreading center. So let's discuss these briefly, because we have discussed them before in these live stream series, and let's eliminate them essentially and not think about them for the rest of the morning. So the Cascades, of course, here in Washington State, we have Mount Rainier and Mount St. Helens. That's a line of volcanoes on the edge of the coast. Or this could be a true oceanic collision where we have two ocean plates colliding underwater, and the result is a line of volcanoes. But this is clearly a plate boundary, right? We have two tectonic plates colliding with each other. One is subducting beneath the other. We generate magma. We create volcanoes. They erupt every few centuries. End of story. So, big X through that. Not talking about that this morning. That's not a hotspot story. Here's another way to create magmas and a line of volcanoes. This time down the middle of the Atlantic Ocean, most famously, but there's a similar line of these volcanoes in the eastern part of the Pacific Ocean as well. This is also a plate boundary, meaning we have two different tectonic plates, and we're generating these big batches of magma at the boundary between two tectonic plates. The difference, of course, is these two plates are moving away from each other, and as a result, we have a divergent plate boundary and a seafloor spreading center, and we have massive eruptions. We have eruptions regularly along the crest of that underwater mountain range, the MidAtlantic Ridge or the East Pacific Rise. X, not talking about that either. There is a third major way to create large volumes of magma, and we don't have to be at a plate edge. That's the first major point. This is really the third and final way that we're generating huge volumes of magma, therefore major volcanism, in the middle of a plate. Sometimes at the edge of a plate, but it's most famous to show massive, I keep saying massive, why? We're showing lots of volcanic activity smack dab in the middle of a tectonic plate, but the plate is moving, and so we're going to get a line of volcanoes, but here's an important difference. The line of volcanoes here, the volcanoes are all about the same age, like the Cascades, right? We don't know which cannon is going to go off. They all have the potential of erupting. Spreading center, different process, different type of a plate boundary. Same idea though, if you want to look north-south, Mid-Atlantic Ridge, there's no age progression here. All these volcanoes are about the same age and they have an equal chance of erupting. You with me? Have you ever thought about it this way? The hallmark of hotspot volcanism within a plate is creating a line of volcanoes, but there's an age progression. Let's slow down and hit this hard. What do I mean, age progression? I think you kind of know what I mean. It means that as opposed to these two situations, our line of volcanoes here actually has a pattern to the ages. In other words, they're not all the same age. We have a line of volcanoes where it's not an equal chance of each of these cannons going off. Instead, depending on the direction of the plate, depending on where the hotspot is located, let's take, we'll still just stay general. So maybe this is a volcano that's active today, and this one was active 1 million years ago, and 2 million years ago, and 3 and 4 and whatever. In other words, the islands get older as you go away from the end of the line. Or you can do it this way too if you want, a different hotspot track, different line of volcanoes. Age progression. The islands get older as you go away from the hotspot, with the implication that a stationary single hotspot, hold on, I heard hotspots were not fixed. I heard hotspots move. Hold on, I heard that hotspots or mantle plumes aren't even a thing. There's a lot of back and forth, but I can't do that back and forth. To have a coherent story for you and to share my main teaching that I've done for 30 years now, I use a fixed hotspot and I use a frickin' hotspot. And I'll just comment on it briefly right now. So I did my master's thesis in the late 1980s at Idaho State University. And my project was to look at the passing of the Yellowstone Hotspot beneath southern Idaho. And I was mapping some normal faults on the northern edge of the Snake River Plain and working out the timing of the basin and range extension and the subsidence of the eastern Snake River Plain as the hotspot passed through. And we all know, I think you know, if you know the basics of this, Patrick probably knows before most of us, that it's not really a moving it's not really a moving hotspot, it's a stationary hotspot. with the moving plate. So here's southern Idaho. I'll do it this way. Here's southern Idaho. Here's a bunch of Mormons growing potatoes, flat field, okay? And here's a stationary hotspot. In this case, it's the Yellowstone Hotspot. I do this so you can still see the hotspot. I guess not. Yeah, like that. Okay? So we're going to have a hotspot that's stationary. It's fixed. It's not going to drift around. And we're going to take southern Idaho, which is part of the North American plate, and we're going to make a whole line of volcanoes, but we're only going to make one volcano active at a time. The result is a chain of volcanoes, a line of volcanoes, but they're not all the same age because we have one fixed hotspot and a moving tectonic plate over the top. That's what I'm trying to show you here. More on that in a second, but my point is, I published that thesis, decent little project, you know, didn't change the world, but it was okay. And 5 years later, Gene Humphreys from University of Oregon comes up and gives a talk here at Central Washington University, and this is back in the mid-90s, you know, we're like using overhead projectors, and he's got all these acetates, you know, and these little markers, you know. I still remember that for some reason. But I also remember him saying there is no such thing as a Yellowstone hotspot. There's no such thing as a mantle plume. I'm a geophysicist. We don't see any evidence for this finger. I'm not flipping you off, this finger. And I was like, what? Well, cut to the chase. You know how these things work, you know. We now have enough CAT scan images, essentially, tomography, to show that there truly is. And I think even Gene Humphreys now is back on the mantle plume idea. But occasionally hear rumblings like that. These hotspots are not really a thing. Occasionally hear rumblings that, oh, you know, the Hawaiian hotspot is not fixed. It's actually drifting itself. I can't do that in my head. I don't get it, and I don't even really want to go there, to be honest. So there, I've kind of shared that with you. So the idea is then that we have a line of volcanoes. Only one of them is active. Yes, I'm talking about Hawaii. Yes, I'm talking about Yellowstone. But these other guys had their moment in the sun. I'll add to this now. So we got some animations from Jenda Johnson we'll look at to help us, but let's just try it old school wise, okay? So we're done talking about this. It's nothing but this the rest of today. So the heat source has to be deeper than the depth of the tectonic plate. So on average, these tectonic plates, these lithospheric shells that are moving, have about a 100 kilometer thickness, 60 miles down. So because we have this fixed mantle plume, it's not moving, but we do have a moving tectonic plate over the top. We're going to have this experience where if you are a portion of the tectonic plate on top of this mantle plume, hotspot, these are the same things, right? Hotspot, mantle plume, same thing this morning. We're going to make an active volcano. But now as we move our tectonic plate over the stationary hotspot, that guy's going to get moved. It's no longer going to erupt. It's dead for good. And in its place, a new volcano will grow. Move them again. You see how this works? If you've never heard this before, you see how this works? You continue to move these volcanoes down the line. You can think of a conveyor belt if you want. You can think of a blowtorch making an active volcano and then moving it off. But these guys had their moments in the sun. Some of us used to be athletes. Some of us, for about 3 weeks in late 1979, could dunk, could dominate in the paint, had the hair, everything was great. It's all downhill from there, man. It's all downhill from October 1979. So we had our glory days. Our glory days is when we were riding high, when we were actually active in building this beautiful big island of Hawaii on top of the Hawaiian hotspot. But as soon as we get out of high school, athletically, it all goes downhill. And now we can barely hobble across the street to scream at the neighbor because their truck is too loud. Okay? Glory days, a slow demise. So in the case of the Hawaiian hotspot, we have sea level, and we do have, when we're in our glory days, when it's October 1979, we are, thousands of feet above sea level. I'm talking about the big island of Hawaii. I'm talking about Mauna Loa and Mauna Kea and Kilauea. But as soon as we get moved off of that hotspot, we lose our magma supply, we stop erupting, and we start eroding. And so as you'll see with some of the stuff that Jen is going to show us, each of these beautiful glory days volcanoes is now completely underwater. It's like a graveyard of old shield volcanoes that had their moment in the sun. Now, what I'm describing is the Hawaiian hotspot and what's going on with the demise of a shield volcano and reducing that to a seamount and having that seamount continue to ride underwater to Russia before it gets destroyed in a trench. How about the Yellowstone hotspot, which I started with, which is again the master's thesis? There's no water now. An important comment is there's a completely different kind of volcano if we have a hotspot burning a hole in a continental plate versus an oceanic plate. Let's try that. So if you're a veteran of these live streams, you've seen me do this a million times, but let's do it 1,000,001 times. There are three main kinds of volcanoes on planet Earth. Shield volcanoes made out of basalt, composite cone volcanoes made out of andesite, supervolcanoes that explode so violently they leave a huge caldera. The difference is primarily the amount of silica that's in the magma chamber. And this applies this morning because if you have a hotspot burning or melting ocean crust, you're going to get this low silica stuff and therefore these low fluid basalts, and that's what the Hawaiian hotspot is talking about. Good morning. If we're at a coastal situation, not a hotspot discussion, we create 60%. But if we have a hotspot melting a continental plate is thicker and made up of totally different rocks, and so we're going to create this very different kind of volcano. So if we have a thin ocean plate over a stationary hotspot, we'll create a chain of shield volcanoes, Hawaiian Islands. If we have a similar hotspot underneath a thick piece of continental crust, we're not going to make shield volcanoes. We're going to make these very humble little hills made out of rhyolite, but those aren't going to last forever. And we'll basically have a huge supervolcano explosion. But it's a hotspot and a moving plate, even though it's a very different type of crust. And so we're going to get a chain of explosions and a chain of calderas. Same concept that I just talked to you about. It's more easy to visualize with our moving Hawaiian plate, our moving Pacific plate over the Hawaiian hotspot. But we're going to get the same kind of pattern of string of pearls, volcanoes getting older as you get away from the hotspot. Hope that you can see that. Let's make a few casual comments verbally, and then I think I want to go right to the visuals. I mean, this is all well and good to get us started, but there's a lot of interesting smaller ideas that fit into this. that you're maybe curious about right now. You're maybe already typing questions, but if you're new to us, we don't really do the live Q&A until at a certain point, so I'm not reading your questions right now. And then again, we get to Roman's video. So I've just discussed a little bit about the similarities between Hawaii and Yellowstone. Iceland is a hotspot, but it's a hotspot at a spreading center. So Iceland has its neck up above the waves of the Atlantic Ocean, whereas the rest of the Mid-Atlantic Ridge essentially does not, because in addition, talking about Iceland now, in addition to this seafloor spreading story and a asthenosphere coming up and feeding basalt along a divergent plate boundary, there's also one of these mantle plumes, one of these hotspots that is adding extra heat. That's all I can do cartoonishly. And so we have an extra amount of basalted Iceland building this island and then splitting it and sending new stuff up. So there is a kind of a different pattern with this age progression at Iceland. If you think about it, instead of the islands getting older and older in one direction, you're going to get islands that are getting older and older in both directions because we're taking two ocean plates and spreading them apart. And you're like, huh? I don't think you lost me now. I can't picture that. We got visuals coming. The Galapagos is another interesting, I think I should do this a little bit. So now I'm talking about two different situations where we have spreading centers with a hotspot smack dab in the middle of it. He's freelancing this morning, ladies and gentlemen. So let's say we're up in the Goodyear blimp and we're looking down through the water of the Atlantic Ocean, and we can see something down there in the water. It's not a whale, it's a ridge. It's not a ridge, it's the Mid-Atlantic Ridge. It's not a passive ridge, it's a place where there is seafloor spreading. You got it? Mid-Atlantic Ridge. And most of you know that if you look at the age of the ocean floor in the Atlantic Ocean, the age of the basalt here and here match. The basalt here and here, age-wise, matches. The basalt here and here, a little bit older, matches. That was an exciting discovery in the 1950s and 60s. Proof that all of the ocean floor of the Atlantic Ocean was created at this crack and then was split and sent packing with brand new stuff coming up each time. I mentioned that this morning because there happens to be one of these mantle plumes right at the Mid-Atlantic Ridge, Iceland. And so we have only one place shaded that's above sea level, where you can live at Reykjavik, you can have your tourist industry, probably struggling right now. But if you split this, just like we talked about with the Hawaiian hotspot, you're going to get off of the burner, like if the hotspot is the burner on the stove, we're going to have thermal contraction. So these are not islands, these are underwater islands called seamounts. And they're going to be progressively older. I'm just making up numbers now. Those are ages of basalt, millions of years old. But I think you see what I'm saying. You can look underwater and you can see mountains that were formed at the hotspot. But in this case, we have two strings of pearls instead of one string of pearl like Hawaii. Now, Galapagos is a little bit different. You've heard of the Galapagos Islands, Charles Darwin, the blue-footed booby. It's an amazing place. I don't even know, I'm not prepared now. I can't remember the orientation. It's something like this. So the Galapagos Islands are a seafloor spreading center plus a hotspot, just like Hawaii. But in this case, we're looking down now. We have two ocean plates that are not going east-west or north-south. They kind of have this trajectory. And so it's the same idea. That we have this string of pearls, everybody being formed at the Galapagos Hotspot, but we have two ocean plates going in different directions, and so we're going to bring older material away. Hope you can follow some of this. I really am kind of loose this morning. Why not? Are you aware that there's a spreading center pretty close to my backyard? Really? Yeah. Washington, Oregon. My backyard is at the star. Tenasket is up here. You remember the Juan de Fuca plate coming at, oceanic Juan de Fuca plate coming at Washington and subducting beneath Washington, Oregon, Northern California. You've heard it a million times. Well, there is a spreading center. There is a divergent plate boundary, a cute little one, that's, I don't know, 500 miles away? I should know. 350 miles away? Don't know. So basically, if you go to Ocean Shores, Washington, and then you start walking underneath the ocean floor, hold your breath, you'll get out to a big mountain range out there. And sure enough, there's a hot spot at that Juan de Fuca Ridge, it's called. Juan de Fuca Ridge, the spreading center. So that means that the Pacific plate is moving to the northwest away from that. So spreading center, Juan de Fuca Ridge, the Cobb Hotspot, Axial Volcano. It's erupting. But my point is, if you look at the Cobb something or other, I can't remember the other word, there's one of those seamount lines, the string of pearls that stretches towards Alaska. Same idea. And I actually had this thought right now, in real time. Why? I'm not sure there is a chain of seamounts on the Juan de Fuca plate heading towards us. Why would that be? But this Cobb Hotspot trail is part of the story. So I'm hoping to anchor you in some field observations with these chains of seamounts on the ocean floor. That's the easiest thing to see because you can still see those seamounts, those pimples, those gumdrops on the ocean floor, all lined up beautifully. And we'll go to the visuals in just a second, I promise. But you might also want to be talking about the origin of the mantle plumes. Why does a hotspot exist where it does? And that's where Roman does most of the heavy lifting. But I'll give you a couple comments right now. We still don't really know why those hotspots exist where they do. There's a couple dozen of these hotspots. It's like take a world map and have 25 darts and drink a lot and blindfold yourself and throw the 25 darts one at a time at the world map. It appears that's the arrangement. And we've had, since plate tectonic ideas have been established for more than 50 years, we've had a lot of people studying the orientation, the location of the mantle plumes. There's no pattern. You're like, hold on, I read, meteorite, asteroid, impact, large body impact, and antipodal whatever, and it's all been looked at. We might be missing something, but it's still a significant mystery why those mantle plumes are located where they are. Is it truly something striking the Earth? Is it something coming from the outer core? Again, I'm going to lean on Roman. I've said his name so much, I hope his name's right. I can't remember if it's the right name, but we'll get to it in a second. In fact, we'll get to it now, okay? Yep, 9:30. So we're going into the cozy fort. I think I can do it by keeping the house intact on top. The house is this cardboard box and blankets and foam So give me a second, talk amongst yourselves. And there's nothing like a quality animation to bring this kind of stuff to life. And that's why there's a huge need for more of that. Accurate, field-based. Jenda Johnson, if you haven't heard of her in Portland, is the queen. But this guy, Roman, apparently I'm deeply in love. Uh-oh. Cozy Fort by Steve, trademark, Cedro Woolley. It's just breezy enough. I'm not going to put the bar on until I have to here. Are we functional, by the way? I'm gun shy from last time. We doing okay? Great. I continue to get lots of emails, too many to handle. That's great. Many of you commenting on the Cozy Fort. It's you know, you really need to go to some whatever switcher relayer thing. I like the Cozy Fort, damn it. You don't want slickness here. You want, well, I'll let you decide what you want. But anyway, it's part of the experience. It's part of the experience. Ah, Cozy Fort. If you missed the origin of the phrase, my dad, who passed away last summer, and as kids, we'd build our forts with all of our cardboard boxes and made cozy forts. That was his phrase. Okay. 830. Okay. So I talk to myself now. I mute myself. I get rid of myself. And we start with a few of my teaching slides that I've used forever with a couple of animations. Let's burn through those real quick. Hawaiian Islands, a line of volcanoes. Why? A line of volcanoes. Why? We're out in the middle of the Pacific Ocean. Do we have subduction? Impossible. We're in the middle of a plate. Oh, okay, that's interesting. They're huge mountains, mostly underwater, but they're still lined up. They're shield volcanoes. They're not supervolcanoes because we're in an oceanic situation. Deep mantle plume. Oh, damn. You kidding me? Seriously? You got a line of those things going all the way to Russia? And we've got ages for the basalt on every one of those underwater seamounts? That's right. They get older and older. I wasn't kidding now. And here's a map of the world. Every red dot is a hotspot. Every red dot is a mantle plume. And you can see some of them are in continental settings, some of them are in the ocean, some of them are at divergent plate boundaries, as we were discussing. And if you're sure you've got the answer, I'm not sure you've got the answer. Just FYI, I'm not sure you've got the answer. Animation time, pretty good one here. Notice they have their mantle plume deeper than the tectonic plate. Kind of a strange little narrow hose of magma, but they're building our Hawaiian Islands one at a time. Basalt, basalt, basalt. No supervolcanoes, but if you were trying to, if you're new to this hotspot idea, this is the visual to have. And I'm going to stick with it because I think, yeah, they're going to get us up in the sky now, looking down on the Hawaiian hotspot. And of course, there's a big bend in the Hawaiian hotspot seamount chain, which catches everybody's eyes And it's not just this seamount chain, by the way. There are other seamount chains that also bend at 43 million years ago. Some say 47. I'm not sure what the discrepancy is there. So it appears that there's a sudden change in the direction of the Pacific plate. But again, there's been some new papers saying that the hotspot is not fixed, and that explains it. I don't understand it, so I'm going to ignore that. Now, if we take another hotspot, similar depth, similar heat, but we're in the middle of a continent instead of an ocean, we're going to have this instead of the big island of Hawaii. We're going to have a supervolcano. But nonetheless, we have a heat source, we have a mantle plume that happens to be in the Rocky Mountains today, making calderas and rhyolites instead of basalt. There's from my master's thesis, handcrafted. And you can see that that eastern Snake River plain is a plain, it's flat, and that's where the Yellowstone Hotspot migrated through. In other words, there's progressively older volcanic material as you go to the southwest, away from Yellowstone Park. So, I think that, oh, we got wind now. I'm gonna hold on. This obviously looks very different. We're making supervolcanoes. We're having mid-crustal reservoirs. We're getting bimodal volcanism. There's all sorts of quirky stuff happening with this, but the main thing I want you to notice that we're still getting a moving plate. We could have used more of that. I don't really care about the supervolcano thing now. Moving on. Okay, so that's the common thread between Hawaii and Yellowstone. I'm U.S. specific, of course, or U.S. centric. Not by design, just that's what I know. Other random stuff I found that maybe you found also. Somebody took let me back up. Somebody took a beaker of water, put some red oily dye in on the bottom, and then took a little candle and started heating up the water. And I like just the look of this so that we can see kind of this mantle plume, this hot spot coming up from significant depth. And that mantle plume is mushrooming at the base of the crust. And Roman does a nice job with that as well. Yes, lava lamp. Muffler boy. Jenda Johnson, I'm a huge fan. If you go to, let me show you the YouTube channel. This is not the one I'm really touting with Roman, but if you go to Iris, what does that say? Iris Earthquake Science? That's a YouTube channel. Highly recommended. There's dozens and dozens of short, high-quality animations. I'm going to get some volume on this one now. This is Roger, who's a little stiff. Roger's a nice guy. He's a little stiff on this one, I think, with narration, but the animation is outstanding. Sorry to shame you there, Roger.
A hotspot is a localized source of high heat energy that sustains volcanism. It is not an isolated shallow magma reservoir beneath the crust, nor is it a pipe of magma that streams from the outer core. One theory holds that hotspots may begin as a blowtorch-like thermal perturbation in a zone between the liquid outer core and overlying mantle about 2,900 kilometers deep. The thermal plume allows solid, yet mobile mantle to rise very slowly and convect outward. Convection is the process by which heated material rises and cooler material sinks. Although magma may be generated as deep as 1,500 kilometers, individual blobs do not traverse the entire mantle. Let's zoom in to look at the onset of hotspot volcanism beneath a moving plate.
Here we go.
As each pocket of melt stalls, its heat is transferred to adjacent rock. This transfer continues to the base of the tectonic plate, where decreased pressure facilitates rock melting.
It's all content from Bob
Butler. The magma that forms at the base of this plate rises through the plate in a network of cracks and shallow chambers and erupts on the surface.
I like what Jenda does here.
Over thousands of years, large volcanoes build on top of the plate.
Nice.
The weight of the volcanoes bends the plate downward. Volcanoes that spent their constructive life over the thermal plume slowly get rafted away on the moving plate, and new volcanoes build in their place. Multiple dikes can feed several volcanoes from separate conduits. The moving plate drags the thermal plume with it. This can explain why volcanoes can erupt again after centuries of quiescence, even after they have moved off the center of the hotspot. However, erosion greatly outpaces volcanism as eruptions wane, and the buoyant effect of the plume diminishes, allowing the volcano to subside.
So I think very highly of Bob Butler, Robert Butler, who's now retired. He was at University of Arizona for a long time as a geophysicist, and then moved to University of Portland and rededicated his career to science education. And he had an amazing program at University of Portland and made all those animations with Jenda Johnson, who I also think very highly of. And I strongly recommend going to that. Bob has this encyclopedic, he knows a lot about a lot of different things. And it's fun to watch him answer questions because he's just so well spoken and thinks so clearly. Another fan, I'm a fan of another person, Christopher Scotese. I've mentioned him before. Here's his YouTube channel. Can you see it in the lower left? Christopher Scotese. He's retirement age, maybe fully retired, but has devoted his life to animations of plate reconstructions and supercontinent cycles, etc. This one's a little rough to look at. I might try to narrate as we look. I think the sound is off on this one. But it shows something I'd never visualized till this morning when I found this. The Reunion Hotspot and the Deccan flood basalts that are 66 million years old. And I've always read about Reunion Hotspot and mass extinction and that sort of thing, but I could never quite picture the geography. And we'll do it a crack with Scotese, and then Roman's going to help us. So let me try to describe what you're looking at. Can you get your bearings at all? We're at Pangea time. That's Antarctica and Australia and India connected together, and Africa is nearby. Can you see Madagascar hooked on to India? Madagascar hooked onto India. Can you find it? I don't know if... There. Now, at 66 million years ago, we're going to get a major hotspot begin. I emphasize, this is showing a hotspot beginning. Here's India. I can't read the numbers, but hotspot begin there. Hotspot begin there. And now as India continues to move north, there's a trail, a string of pearls of seamounts in the Indian Ocean that get progressively younger as you get towards the present location of the Reunion Hotspot. So flood basalts in India, and basically India, a continent, is drifting over a deep hotspot. I never had that geometry in my head. And you're like, oh, I guess I kind of got that. That moved kind of fast for me. Well, now I think we're finally ready for, what's this? Hang on, what's this? No, we don't want that. So the last thing I'll show you is, I'm going to read this. So this is Facts in Motion. Facts in Motion, YouTube channel. And I'm going to click on, am I going to do this? Yes. I'm going to go to his little segment, his little tab that says About. And I'm going to read it to you. He's from Germany. My name is Roman, and this is my YouTube channel. I'm mostly focused on scientific and educational videos, whatever I currently find interesting. I do everything myself. Research, writing, voiceover, art design, animation, and sound design. So don't expect too much in terms of quantity. This all takes a lot of time and effort. At least one video a month is what I'm currently aiming for. So I know nothing about this guy. I don't know anything about his background. Maybe that's by design. He started this in 2017. I'm just imagining Roman in his apartment in Dusseldorf. I don't know, just kind of making this stuff. I don't know if he's a geologist or what the story is, but what he has created, and it's not just geology, by the way. It is top drawer stuff. So this is a 17-minute video that's actually part 2 from a large igneous province program he did, which was an equal length. And so I'm just gonna grab a couple 2-minute segments here that I think are particularly powerful and helpful that add to what we were doing already. So be prepared for me to kind of skip around a little bit. I hope you can handle that. And then we'll go to your live questions and answers.
Or more specifically, what causes these cataclysmic eruptions?
He's got this kind of Mission Impossible kind of vibe. It's like, should you choose to accept your mission, Dr. Zentner, would like you to go to Issaquah and eliminate Dale. Yes, I know he has firearms, but you must exterminate everyone.
That's what we will explore today. The exact processes are of course still subject to heated debate, but the principal model for their origin, which is widely accepted today, is the so-called mental plume model. Before we can discuss what exactly this is, however, we first have to understand how volcanoes are typically formed. Almost all volcanoes on Earth are the result of tectonic processes and are formed either by 2 colliding plates or 2 plates drifting apart. Subduction zones are convergent boundaries where the edge of one plate, usually a denser oceanic one, is forced under the edge of a less dense plate and then pushed into the mantle. During the subduction, the downgoing plate experiences increasing pressure and temperature. At depth of around 100 kilometers or 60 miles, the pressure is great enough that water inclusions trapped inside the rock are freed and released into the overlying mantle, which lowers the melting point of the already hot mantle rocks, resulting in partial melting. This process is called flux melting, and the magma it produces then slowly rises into the crust above and finally to the surface, forming a chain of volcanoes alongside the subduction zone.
Not our topic yet.
In contrast, divergent boundaries are zones where 2 plates move apart. Here, a spreading ridge, either in form of a rift valley or mid-ocean ridge, is created, through which hot mantle material can rise to the surface.
I love you, Dale.
This also reduces the melting point of the rocks, this time as a result of decompression melting caused by the reduction in pressure during the ascent. The resulting magma then leaks onto the surface, cools and creates new ocean floor in form of giant undersea mountain ranges. But how do mantle plumes fit into this picture?
Here we go.
Surprisingly little. The volcanic processes we just covered are all the result of mechanisms inside the uppermost layer of the Earth, roughly the first 100 to 200 kilometers. Mantle plumes, on the other hand, have a much deeper origin. They are columns of enormous quantities of hot rock, upwellings that rise to the surface from the depth of Earth's mantle, 2,900 kilometers or 1,800 miles below our feet. As such, they are part of the ongoing convection processes that take place in the mantle, in which hot material from inside the Earth continuously rises below the tectonic plates, cools and moves back down again, similar to what happens inside a lava lamp, just way more complex. Because the mantle consists for the most part out of solid rock that only behaves like a fluid over geologic time frames, these processes are of course very slow and take millions and hundreds of millions of years.
This guy's showing solidus and liquidus curves on this frickin' thing.
Mantle boundary. Here in the thermal and chemical boundary layer at the base of the mantle, which separates the liquid outer core from the solid.
Couple more segments. Oh yeah, this is like health class now.
The mantle plume forms. As it ascends through the mantle, it slowly starts to take on a mushroom shape, because the hot material rises faster through the plume than the plume itself rises through its surroundings, not unlike during the explosion of a nuclear bomb. Most plumes never make it to the surface before they cool down again and lose their momentum, but some of the largest can rise all the way through the mantle and below the lithosphere. When such a plume hits the tectonic plates, which act like a barrier, it flattens out and deforms into a thinner, wider disk. As we have discussed before, the reducing pressure will eventually reduce the melting point of the hot solid rock so much that it begins to melt. This produces enormous quantities of liquid basaltic rock, basically a giant bubble of magma with a diameter of multiple hundred kilometers directly beneath Earth's plates. From here it will start to rise into the crust, build up in countless magma chambers, and ultimately produce large-scale flood volcanism on the surface.
Okay,
This can go on for a few 100,000.
I got a couple more things. Oh, they're leaving on a hike. Where are you guys going? Left in the dust. All right, so that I could have done on my own. But this is what Roman is a great help for. Terrible grammar, forget that.
This explains, for instance, the formation of the Hawaii Emperor chain, a chain of around 130 dormant seamounts stretching over 5,800 kilometers across the Pacific Plate, like a string of pearls, with the Hawaiian Islands at the end. Other hotspots follow a similar pattern. Yellowstone, for instance, has, over the last 15 million years, slowly moved eastward as the North American plate moved westward over the hotspot. Follow this trail of breadcrumbs and you can see an image of the volcanic activity through time. When you reach the point in time 16 million years ago, the position of the Yellowstone hotspot on the North American plate overlaps suspiciously well with the Columbia River basalt group. This suggests that the hotspot was responsible for the enormous flood basalt province that formed between 16 and 9 million years ago, when the Plume head hit the lithosphere, and that since then the tail of the Plume was responsible for the regular supervolcano eruptions. In Hawaii's case, however, you can't trace the breadcrumbs back to a large igneous province, as the subduction zone of the coast of Russia has already destroyed all evidence of its existence. On first glance, you might think, doesn't the trail point perfectly to the Siberian traps? This is true, of course, but only a coincidence. Once you cross plate boundaries, you also have to consider the position of the plates relative to one another.
This guy is so good.
And the Eurasian plate was, of course, at no point in time over today's Hawaii. At least not in the last 500 million years or so.
Who is this guy?
In fact, no continental plate was. The Hawaiian hotspot was always surrounded by oceanic plate. When exactly it happened, and how destructive its first eruption was, we will therefore probably never find out. For other hotspots, this is however still possible.
Here we go.
The reunion hotspot of the coast of Madagascar, for instance, can be linked to the Deccan traps. When 66 million years ago, the Indian plate on its way to its current position moved across the hotspot apparently right as the Plume had hit the lithosphere, the resulting eruption then formed the massive lava province that even today covers nearly a third of India.
Amazing.
The some 4,300 kilometer long chain of seamounts produced by the Louisville hotspot may point towards the Ontong Java plateau, while the Iceland hotspot was likely responsible for the formation of the North Atlantic igneous province.
This guy's out of control.
Connections like these aren't always possible. The Siberian traps, for instance, can't definitively be linked to a present-day hotspot. Iceland, as well as the Ural Mountains, are proposed locations of the Plume today.
All right.
But it's also possible that its corresponding hotspot already went dormant in the past.
I mean,
We have learned where and when.
you can spend hours trying to, create that in a classroom setting. And that guy did, an amazing amount in like 40 seconds. So I'll reel myself back in, I promise. But I got to show you more. Here he comments on how the seismic tomography has helped confirm that these mantle plumes are a thing. This is quick, I think.
About the physical properties of the subsurface.
Hang on.
While the models these scans produce have at the moment still a very poor resolution, they have at least finally confirmed what for a long time was only conjecture, namely deep mantle plume-like structures under most major hotspots like Yellowstone, Hawaii and Iceland. But these are obviously only still images of convection processes that take millions of years. To fully understand the formation of mantle plumes and flood basalt provinces, it therefore still requires a lot more research. But large igneous provinces are of course not only of geological importance,
Here we go.
but also of biological interest.
Bring it, Roman.
What catastrophic impact the formation of such provinces can have on the planet, we have already discussed in the last part, using the example of the Siberian traps.
Do it.
But this was by no means an isolated case, quite the opposite. If you illustrate the formation of the largest flood basalt provinces of the last 500 million years graphically, you can see a striking temporal correlation with the boundaries of geologic time periods. These boundaries are defined by abrupt and significant changes of Earth's biosphere and climate and the planet as a whole, and often mark the point of catastrophic mass extinctions. The formation of the Deccan Traps, for instance, falls almost perfectly on the Cretaceous-Paleogene or KT boundary that marks the extinction of the non-avian dinosaurs. The formation of the Central Atlantic Magmatic Province overlaps with the Triassic-Jurassic boundary, and the formation of the Siberian Traps coincides, as we have discussed, with the Permian-Triassic boundary and the end Permian extinction. At the end of the Devonian period, the Earth also experienced this kind of volcanism, in fact an exceptional amount of it. It is speculated that this was the result of the arrival of a super plume under the East European platform, resulting in the formation of at least 4 flood basalt provinces over a relatively short 20 million year time frame.
Damn.
Although the timing and importance of the individual events is in this case still poorly understood, it might be an explanation for the series of smaller extinction events typically combined into the late Devonian extinction. Particularly, the formation of the Willowy Traps seems to correspond well with the so-called Kellwasser event, the first and most severe of the late Devonian extinction events. Together, these 4 boundaries describe 4 of the 5 largest mass extinctions in history, each responsible for the loss of 70% or more of all species and probably 99% or more of all individuals. Even the 5th and earliest of these so-called Big 5 can be linked to large-scale volcanism due to elevated mercury concentrations in the Ordovician rock layers, although a corresponding lava province seems to no longer exist.
God.
After the discovery of the
All right. Nope. I got to show you this because you're going to be asking about this.
Chicxulub crater in the mid-20th century and the realization that an asteroid likely was what had wiped out the dinosaurs, the consensus in the scientific community subsequently became that asteroid impacts must be the main driving force behind mass extinctions in general. Today, however, thanks to intensive research on the formation and role of large igneous provinces over the past few decades, we now know that this is likely not the case. Asteroids certainly had an important impact on this planet, but it simply can't be a coincidence that all 5 of the largest mass extinctions in history, as well as many more or less dramatic changes of our planet, all happened at the same time as some of the most catastrophic lava eruptions the world has ever seen. Advancements in high-precision dating, both of the mass extinction events and the formation of the corresponding flood basalt provinces during the last 20 years, have in almost all cases only strengthened this temporal link, and the examination of the events individually has in most cases confirmed volcanism as the main cause for the extinction, and not, as previously thought, asteroid impacts. Even for the case example, the extinction of the non-avian dinosaurs, we now know that large-scale volcanism has at least played a role.
I've already said how impressed I am. And I'm going to do one more thing before I close this up and we go to your questions. Roman, this was published. By the way, people keep asking me to post all sorts of links and stuff. You might have to actually do something, okay? You might actually have to, go to Facts in Motion and find this video. So this was 6 months ago, and Roman puts a kind of a pinned comment under this and says, I probably have to, so in other words, he's commenting on his own video because he's been reading all the comments on his, portions of what we just saw. Roman speaking, I probably have to address a thing that was mentioned a lot in the comments, and that is the hypothesis that asteroid impacts have caused flood basalt eruptions. In other words, tied to hotspots. It usually goes something like, a large body impact can trigger flood basalt, volcanism, and topodily on the opposite side of the Earth. Because the seismic waves caused the impact are focused there. This general hypothesis garnered attention in the 1990s when the Mantle-Plume model wasn't yet so widely accepted, and before we knew much about the formation of these provinces. Since then, however, there wasn't any major breakthrough or even progress in confirming this hypothesis. We don't need an outside force to explain and model large igneous provinces, and to this day we haven't found a single convincing example of a crater that can be linked to the formation of flood volcanism. The 3 most quoted craters from the comments are Bedout, B-E-D-O-U-T, which was originally dated to around 250 million years ago and supposed to be caused to Siberian traps. This dating is, however, controversial and probably isn't even an impact crater. The Wilkes Land crater in Antarctica, which also dated to some 250 million years old, isn't any more convincing either, and the last serious papers make a connection between this theoretical impact crater and the end of Permian extinction is, I think, from the late 1990s. Lastly, there is the Chicxulub impact, which, as we have discussed, definitely did not cause the Deccan traps in India. Plus, it wasn't even antipodal to begin with. That we haven't found any good examples isn't really surprising, since models have shown that it's very unlikely that the impact of even a large asteroid would be seismically powerful enough to cause such a phenomenon on its own. That's why this hypothesis is seen at best as controversial today, and why I didn't talk about it in the video. But since this popped up so much in the comments, I thought I'd still address it. The only hypothesis that is still discussed and backed at least by some evidence is that the Chicxulub impact worsened the Deccan traps in India, volcanism, based on the fact that some 70% of the lavas were expelled after the impact. This can, of course, simply be a coincidence, but it's also not hard to imagine that if there already was an enormous amount of magma trapped close to the surface produced by a mantle plume, a hotspot, the seismic waves caused the large impact could have certainly freed them. So this hypothesis is, I think, far easier to get behind. All right, so if you tuned in for a hotspot volcanism live stream and wanted to get into impacts and antipodal stuff, we can still go there with your questions right now, but I think Roman's done the heavy lifting for me there, and I instead am excited to talk about what I know about hotspot volcanism beyond some of the basic field relations that I shared with you earlier. And it's already 10 o'clock. That was a long one, hadn't planned on that, but Roman Facts in Motion YouTube channel. It's time for some live Q&A, 15 minutes or so. Actually, I think I have another hour since I missed the boat. Maybe they left a note for me on the kitchen counter on how to find them and join them on the hike. Or maybe not. I think my wife actually said the other day when I did a bunch of these live streams in the front porch, I'm tired of hearing your voice. And I said, wasn't that in our wedding vows? Didn't we write our own vows? Didn't you include that? I'll live with you even though I'm tired of your voice. JK. Okay. Give me a second, please. We'll pop out the chat like a boss. Right between the eyes. Top chat? No, I don't play top chat. I'm a live chat guy myself. That's how I roll. Bijou needs to get in. Hang on. Morning. I appreciate you being with us this morning. Getting hassled by neighbors walking down the sidewalk. Andrew, do islands on top of spreading ridges split in half? Will Helsinki's island split in half? I don't know about Helsinki, Finland's island, so I'm sorry I can't help you there. I'm intrigued. In general, those seafloor spreading centers do split and new magma comes up, but it's regional. It's not down to the case where you have a mountain and the mountain suddenly cracks in half. But many of you who've been to Iceland and have visited the place where you can put 1 foot on the North American plate and 1 foot on the Eurasian plate, pretty amazing, and that split in places is truly a knife edge right down the middle here. Kevin, what happened to the hotspot that formed the Jemez caldera in New Mexico? Did it just go away? I'm confused by a lot of things. Grab that one, Kathy. We did have a session on supervolcanoes in New Mexico, in Utah, in Eastern California. Are there mantle plumes associated with each of the supervolcanoes in a continental setting? Seems like there should be. But then why don't we have a similar Snake River Plain-like trail away from each of those sources? I've never heard an answer. I've never heard any discussion even of that. Why does the Yellowstone heat source, well, so I don't know about any of those mantle plume signatures in any place except the Yellowstone system for North America. And if you've been waiting for it, I'm a fan of taking the Yellowstone Hotspot all the way back to 56 million years ago when we create Silesia off the coast of the Pacific Northwest. Not everybody buys that, but there's enough research, in my opinion, that suggests that the Yellowstone Hotspot was a thing out in the Pacific 56 million years ago, making shield volcanoes, and then North America's continental crust drifted over the top, kind of like how the India scene, well, kind of, but kind of not. All right, let's keep it moving. Bill, could I discuss what caused the bend in the Emperor Seamount chain? For years, Bill, I don't. So if this is the Pacific Ocean basin, and here's Hawaii, and here's the chain of seamounts, each of them formed on the Hawaiian hotspot. Actually, an exam question I've had for years. Based on the Hawaiian Emperor Seamount chain, for 70 million year record of the Pacific Plate moving over the Hawaiian hotspot, how was the Pacific Plate moving 70 million years ago or 60 million years ago? And I've always taught that the Pacific Plate used to move more northerly, and then suddenly at 40, I'm not flipping you off, 43 million years ago, it suddenly changed its direction and started going northwest, as it does today. Again, there's been some papers in the last 5 years to suggest that there's a movement of what I consider the fixed hotspot, and that explains some of that, but I don't understand that. So from my point, I still just kind of teach it as there was a sudden change of direction of the Pacific Plate's motion. And the obvious question is, why did it change its direction? And I've always meant to follow up on this, and I haven't. I think the timing of India first colliding with Eurasia to start forming the Himalayas is about the same time that we have this bend. I've never really taken the time to follow through on that. But Patrick, age 6, is the Juan de Fuca Ridge hotspot younger than the Yellowstone hotspot? Does it have anything to do with Silesia, or is that just a Yellowstone story? Good job, Patrick. The Juan de Fuca Ridge is a remnant of the much larger East Pacific Ridge, or East Pacific Rise. I don't think it's an accident that the Yellowstone hotspot was on the East Pacific Rise. Wait now, is that true? The short answer, Patrick, is the hotspot that's on the Juan de Fuca Ridge is too young and not the same thing as the Yellowstone story. But what I'm hesitating on, and your question is an excellent one, if we go back a certain amount of years, do we have a spreading ridge out in the Pacific with two hotspots on it, the Yellowstone hotspot and then possibly this Cobb hotspot? I've never thought of that. I'll have to look into that. Thank you for the question, Patrick. You're a winner. William, could a hotspot be the remnant of a spreading ridge that is now under the craton of a continent? Oh, Lord. Could the hotspot be a remnant of a spreading ridge that is now under the craton? Oh. Yeah, that was a surprise. I forget which limestream that was, but we went through this whole thing about the Chalice volcanism and a spreading ridge being subducted, and so many of you were so interested in what is going on. is a spreading ridge still active once it slips beneath a continent? And that's kind of what William is asking. I can buy it, William, except that a spreading ridge is such a linear feature. It's such a widespread area of volcanism. And I don't see how you can get a line of volcanism and get it down to a single point. And I also think, I'm not a geochemist. Did I say that right? I'm not a geochemist, but apparently there's a helium isotope that shows up in volcanic rocks that indicates it's a kind of a smoking gun for mantle plume generated magmas as opposed to spreading ridge. So there's even a geochemical signature that apparently is different with spreading ridge versus mantle plume. But I'm out of my element. Har har, there. Helen, so are the igneous provinces the beginning of a hotspot breaking through the crust? So the large igneous provinces, are the large igneous provinces the beginning of a hotspot breaking through the crust? Well, that was definitely the story with how Roman discussed it, wasn't it? With the Deccan traps. The Siberian traps. I guess so. I don't know. Interesting thought. Wish I could give you a better answer there, Helen. Troy, is there a connection between the Hawaiian chain direction and the disappearance of the Kula plate? Oh, I love what you guys are doing. I've already forgotten that work I was doing on the Kula plate. Let me... The Kula is disappearing about the time as at this kink. Yeah, it is. Really, really, really great stuff. Thank you. These are more questions that will help kind of steer me to read more, I think, as opposed to being an actual public servant this morning. Can you explain the plate actions around Antigua and Barbados? Oh God, so I'm really thank you, Chuck. As well as the Sandwich Islands, it looks like the Pacific plate had poured its way over the Atlantic, possible asteroid impact. Are you effing with me, Chuck? I don't know anything there. I'm sorry. Jack, what theories exist of the major tectonic that caused everything that happened 50 million years ago? Pacific plate direction shift, Silesia, Rocky Mountains building stopped. We're kind of off track now because, thanks for the question, Jack. The first live stream I ever did, St. Patrick's Day, you might find it. The buffering quality was not good because I didn't know what I was doing. I was positioned way over there by those oil derricks. Haha. And I was talking about that. And that was a long time ago, and I've forgotten the details. That was a lecture I'm working on, and I haven't thought about it 1 second since then. But there is some timing about a major change in disappearance of plate in North America overriding a spreading ridge in the Yellowstone Hotspot in the story there. There's a lot going on about that time. So in general, I like your thinking, but I, quite frankly, can't remember some of that stuff from 2 months ago. I've noticed that some Columbia Gorge-like rock south of Mount Hood. Is that possible when maps don't show them going through there? Nathan, I don't see how that's part of our discussion today. Those are probably Columbia River Gorge lavas, but Columbia River basalt lavas. What is known about the two calderas in the northern Cascades, like the Kulshan caldera? Thank you, DW. You remember, was it just last live stream? Yeah. The Titan Andesite episode, I was asking, what's going on with, I like somebody's comment, the Roaring 20s. Like there's a bunch of spots in the Cascades near White Pass where there's all these stratovolcanoes standing close to each other, but a couple of them had pretty big calderas. And the question from DW is, there's the Kulshan caldera, and I guess there's another one up there that I may not know of. Is there some kind of intersection between mantle plumes and cascade volcanism? Never had this thought till this very moment, but if we have hotspots at spreading ridges, Meaning if we have some hotspots at a divergent plate boundary, honestly, this right now, is it possible to have a hotspot at a convergent plate boundary? Like, are there truly hotspots in addition to a volcanic arc from a subduction zone and a convergent oceanic versus continental plate boundary? Never had that thought, but I've teased with the idea because of these exceptionally large, even Crater Lake is such a huge event compared to most of the rest of the Cascades as we understand them now, as we look at the scale and the depth of the deposits, etc. So there might be something in the works there. I honestly don't know if anybody's done any work on that to talk about supervolcanoes and therefore mantle plumes in the Cascades. But if somebody knows about a paper, I'd be very interested to read that. Do you think the Juan de Fuca plate hotspot will become another North American hotspot when the North American plate overtakes it? Yeah, I do, Carol. That's a good thought. Assuming that these mantle plumes are stationary, North America will continue drifting southwest, and so that hotspot will eventually be burning a hole through British Columbia. And speaking of that, I've heard all sorts of crazy stuff about volcanism in the British Columbia. I know nothing about. It's a day's drive away from here, and I'm embarrassed to say I rarely cross the border. That's got to change. A few more. It's almost 6:20. Scrolling problems. What else is new? Margaret, age 10. Do we know why the plates can move at all? Margaret, thank you for the question. These plates are definitely moving, and I know that you know that. We have instruments, the GPS receivers, we have satellites, we have ways. So it's not an idea that these continents are moving and that the continents are part of bigger things called tectonic plates. That's a for sure. But you're asking, Margaret, about what is actually causing the plates to move. And you look at animations, even from the esteemed Roman, and he's showing convection. Margaret, if you do this with your finger, that's drawing a circle, right? Well, the thought is that there's this very slow but steady circling of solid rock in the mantle. And that convection in the mantle is driving these plates. I don't know enough geophysics, Margaret, to understand if that's the sole reason for the movement of these tectonic plates. But from my point of view, it feels like, ironic to be a science person and talk about my feelings, but it feels like that's one of those areas where, you know, you got somebody coming in who's a crackerjack and they go, oh, I can't believe you guys didn't figure this out before. Here's why the plates are moving. You know, if nothing else, in freelance now, many of these live streams, you know, Rocky Crandall and others, they come from a totally different angle. They have the ability to visualize and to find all this field data to support their idea and confirm it with the scientific method. And of course, here we are in 2020, and think of how many major things will be sorted out in the next 100 years. And it might be what's driving these tectonic plates. But geophysics, thinking massively, technology, tough to know where we are. Thank you for the question. Gary, is there any correlation between the periodicity of magma plumes and the Milankovitch cycles? Well, that's a creative thought. My short answer is no, because the magma plumes are pretty much regularly producing magma. Like the eruption in Hawaii has been going on nonstop, day and night, since 1983. I don't see the connection there, but maybe you're onto something that I'm not. AZ, what do you think will happen after the Juan de Fuca hotspot? Oh, just talked about it. NM Hockey Fan. is there a thought that some large igneous provinces like the Siberian Traps might be large mantle plumes, hotspots that are short-lived? Yeah, Roman mentioned briefly there's no obvious mantle plume that still exists somewhere in an ocean that you could see where Eurasia drifted away from that plume situation, like India leaving the Reunion hotspot. So it brings up a question that the hockey fan has. Let's go back to our 24 hotspots. Have they always been there? Like the Earth was created and the hotspots were there? Or do hotspots begin? And if hotspots begin, do hotspots die? Can you go to a place where the hotspot just fizzled out? And is that the story with Siberia, which is clearly the biggest large igneous province? It's not even close, which was fueled by, must have been some kind of mantle plume. Don't know. 3 more and we're done. John, could the dikes from the Columbia River basalts be pinning the North American plate in place because the clockwise rotation? I would think of the opposite, John. There is a tie, and I've done this before. Why not? That's how we'll finish. I got a chalkboard, let's use it. And the wind is picking up. I'm going to put this laptop down. I don't want it to blow off. That was too much I don't know in the question and answer anyway. Let's do something I actually know quite well. This will be a quick and dirty version of something that I put on YouTube, I don't know, 5 years ago, called Yellowstone Hotspot and Liberty Gold. And I'll do it very quickly to tie a mantle plume, the Yellowstone mantle plume, the Yellowstone hotspot, with much of the geology that we see here in the Pacific Northwest. And even if you've heard it before, maybe this will be fun to just use as a recap for what we're doing. Okay, states of the American West, the Pacific Northwest. Yellowstone Hotspot is located right here. I'm putting a circle because the Yellowstone caldera is the most recent explosion from these supervolcano explosions tied to the mantle plume that we call the Yellowstone Hotspot. But North America has been drifting to the southwest for a long, long time, and as a result, little Nicky Zentner was doing his master's thesis on the passing of the Yellowstone hotspot, indicating it looks like the hotspot's doing this, but we know that it's a fixed stationary hotspot and the North American plate's moving over the top of it. For a long, long time, I would teach that the hotspot began 17 million years ago in northern Nevada. The mantle plume, just our topic tonight, this morning, whatever it is. 17 million years ago, that thing formed in northern Nevada. And 17 million years ago, major fissures that fed the flood basalts of the Pacific Northwest, the German chocolate cake, the Columbia River basalts. This is ground zero for not only the Yellowstone hotspot story, supervolcanoes, high silica rhyolites, but also these cracks are propagating in a way. So what is the story here? Is this truly the birth of the Yellowstone hotspot to explain all these fissures, all these dikes, all this German chocolate cake, plus this Yellowstone hotspot story? That's what I would teach forever. And then 5 to 7 years ago, I met Paul Hammond, who we talked about last time. And Paul Hammond, on a napkin at a Geological Society of Oregon meeting that I was at, sat next to him at the dinner. And Paul said, let me show you what I've been working on. And on the back of a napkin, he drew out the Yellowstone hotspot going back 56 million years. And he said, I think the Yellowstone Hotspot used to be out in the Pacific Ocean. And I think since that hotspot was out in the ocean, it created the Silesia, the large igneous province known as Silesia. But as North America, so 56. So in other words, instead of the Yellowstone hotspot starting 17 million years ago in northern Nevada, Paul and now many other Oregon geologists are seeing that there may be a story going back 56 million years ago and having the Yellowstone hotspot actually out here straddling some sort of seafloor spreading ridge. But the point is, as the North American plate started crossing this stationary Yellowstone hotspot, in other words, this is now here, not because the hotspot moved, but because we dragged the continent over this stationary hotspot. Paul says, I think there used to be a trail of supervolcano calderas created by the Yellowstone mantle plume through Northern California, going 45, 40, 35, 30, 20, 17. In other words, this trail goes back further. And I think I probably said, well, where are those calderas? They're not there now. And he said, well, what was your name again? Nick? Dick? Is it Dick? No, it's Nick. Mick? No, Nick. It's like I'm calling Campus U Totem for a burger. Deluxe burger basket, no cheese, fry sauce for the fries. What's the name for the order? Nick. Dick? No, it's Nick. Nick. So I gave up. I just say my name's Jerry every time I call. Order for Jerry. So Paul said, what is it? I said, Nick. He said, okay, Nick. Ever heard of this clockwise rotation? Ever heard of this fact that we've had this whole amazing crustal rotation around Pendleton, Oregon? Those calderas aren't in Northern California anymore. Jerry? We have calderas all through Central Oregon because those calderas from the Yellowstone hotspot used to be lined up and they've been moved varying amounts based on the clockwise rotation. And I kissed him on the cheek and said good day. And I've been spreading the gospel of that since then, including the Crooked River caldera 29.5 million years ago at Smith Rock. So that's an evolving story. There's helium in those rocks indicating a mantle plume story. So yes, we can even have a mantle plume discussion with a oceanic mantle plume overridden by a continent in the past. And as Patrick and a few others pointed out, that Cobb hotspot where the Axial volcano is today, never even thought about it till this morning, but we'll have the same kind of override in the future there. A toast to you. And if you so choose to join us tomorrow morning, we're talking about an entertainer by the name of Bing Crosby at 9 a.m. Pacific time tomorrow morning, Sunday morning, out here in the backyard. And I will explain. Here's to you and your health, the health of your parents, your grandparents, your children, your grandchildren, your aunts and uncles, your nephews and nieces. Here's to them, here's to you. Sincere thanks to you for joining us this morning. Hope that you enjoyed yourself, maybe learned a few things, and discovered a couple new YouTube channels to enjoy. Enjoy today. We'll see you tomorrow. I love you. Goodbye.